Hey everybody, Morgan here. So we are on page number 5 of the thermochemistry outline for Honors Chem. And I got to tell you that this is a tough idea that we're going to be dealing with here. Back in page 1, I believe, we defined heat. And we said that heat is a transfer of energy between two objects at different temperatures. Now today we're being faced with a challenge because we showed you in an outline previously that when you heat up a sample of, let's say, solid water, it only rises to a specific temperature and then the temperature stays the same. Now, I know that if I put a whole bunch of ice in a pan and I put it on my stove with a flame underneath it, it will start to melt pretty soon. And if I keep it well mixed and I monitor the temperature of that water while the ice is melting, it stays the same. Except by the definition I just gave you of heat, that means no heat is moving. That means it's not being heated because the temperature is staying the same. Reality, I know that flame is still underneath that pot. I know heat has to be going into it. There's a problem with the definition, not with the chemistry. So to deal with that, we have a new term today, and this term is latent heat. Now, some people call latent heat the heat that causes phase changes. Or what we can also say is that it is heat that does not cause a temperature change. Latent as a root word means hidden. So it's like this is hidden heat. Okay? Now, there are only two latent heats that we define for a substance: the heat of fusion and the heat of vaporization. The heat of fusion is the heat required to melt 1 mole of a substance at its melting point. Now what that means to us is that we don't have to heat it up from a very low temperature to get it to the point where it's going to melt. This is just the energy that goes into melting it. Often this is called delta H naught fusion. Okay? Now, there's also heat of vaporization, which you can probably figure out. It is the heat required to boil 1 mole of a substance at its boiling point. And this is often called delta H naught vaporization. Now, this might be somewhat misleading to you because when we come back to this page, we've covered melting and we've covered boiling. Well, what about condensation, freezing, deposition, and sublimation? Actually, we've covered them also. It turns out that the heat of fusion is positive. Now, the opposite of the heat of fusion would be the heat of freezing. It's the exact same number as the heat of fusion, except it's a negative sign. It's energy that's being taken out. For condensation, it's the same thing as vaporization. It's just that we are taking the energy out. It's being released. Now for sublimation, we just add these two numbers together. For deposition, we add them together and we put a negative sign on it because that's heat that's going to come out of the system. Okay? Now, let's look at a bit of an example here that can help us kind of keep track on what's going on. So, we have 100 grams of water. It's at negative 15 degrees Celsius. We're going to heat it up all the way to 110 degrees Celsius. How much heat does this require? Well, it actually requires us to do several calculations. The first of which is Q equals mc delta T. We have 100.0 grams of water and times the heat capacity of solid water, because down at this temperature, okay, that's a solid. Now it turns out we'd look these numbers up. It's 2.06 joules per gram degree Celsius. And the temperature change is going to be 15 degrees. And I say 15 because if it's at negative 15, I can only heat it up to 0 degrees. Because at 0 degrees, it is going to start melting. And when I run all that through my calculator and I cancel the grams and I cancel the degrees Celsius, this equals 3090 joules. Okay? Now, how about for melting? That's what's going to happen to the solid next. Basically just say Q equals mc. We leave off the delta T, because delta T is actually 0. And I have 100.0 grams. Now I'm just going to go and look up what the heat of fusion is for liquid water, or for water, and it's 333.5 joules per gram. The grams cancel, and this takes 33,350 joules, which is quite a bit more than heating it up those 15 degrees. It's substantially a lot more. Now for Q3, mc delta T, that water that's now at 0 degrees Celsius, liquid water, can be heated all the way up to 100 degrees Celsius. So this equals 100.0 grams times, and the heat capacity for liquid water is 4.184 joules per gram degrees Celsius. We always provide you with these constants, don't worry. And the temperature change at this point is 100 degrees Celsius. It goes from 0 to 100. Celsius cancels, grams cancels, and this time I'm getting 41,840 joules. That is a substantial amount of energy. Okay. Now to boil it, we're back to Q equals mc without the delta T, because, hey, there's no temperature change. So 100 grams times, and I look up the enthalpy of vaporization, or the heat of vaporization, okay, for this, and it turns out to be 2258 joules per gram. Grams cancels, and this equals 225,800 joules. That's a lot of energy. It takes a lot of energy to boil water. And then since I'm going all the way up to 110 degrees, what I can say at this point is Q equals mc delta T, okay? And that equals the 100.0 grams. And I look up the heat capacity for water vapor. It's 2.02 joules per gram degrees Celsius. And the temperature change is 10 degrees Celsius. And this comes out to be about 2,020 joules. So the heat that's required to accomplish all of that is just all these numbers that are added together. So Q total equals 306,000 joules, which is also equal to 306 kilojoules. All right. And that's the strange world of phase changes. Thanks for tuning in. This is Morgan signing off.